Next up, we are going to build the calculator that we just described on the whiteboard. So we're going to start off by opening up the file that's going to have our main function in it. And we're going to include standard I/O because we need to printf our result. This is another program where we're not going to use the command line arguments. What we are going to do, though, is go ahead and allocate a buffer of 100 bytes on the stack. And that's where we're going to read in our line. There's no technical reason why we couldn't handle larger line buffers, but 100 characters is wider than I can type into a terminal window. So that should be plenty for testing and plenty to prove the design strategy for the rest of the program. Now, we're going to loop forever. And while we loop forever, the next thing that we're going to do is we're going to read in one line of text from the keyboard. Now, in order to read in one line of text, we're going to use this function called fgets. If you explore around a little bit in the standard C library for how to read a line of text, especially if you start Googling how to read a line of text, a function that you're going to come across is a function called gets. Now, gets says it gets a string from standard input, and the core thing about this function is this first line of the description, which says underlined, never use this function. That's important. You really should never use the function. It does let you pass in a buffer, a pointer to a place where it could put characters, and then it will attempt to read in one line of text from the keyboard, and it will put the data that the user enters into that buffer. There's one problem, and that problem is this function provides no mechanism to let you specify how big the buffer is. So if you allocate a buffer of size 40, and the user types in a line that is 80 characters long, it's going to fill in the buffer with the first 40 characters, and it's going to fill in the memory immediately after the buffer with the next 40 characters. That's called a buffer overflow. It's a horrible security problem, and more practically, it's just going to make your program immediately crash. But it's just a bad idea. This is one of the reasons why C programs are notorious for being insecure, is functions like this just in the standard library waiting to get you. And so don't use gets. Instead, we have this function fgets, where we can specify the buffer, the size of the buffer, and then additionally we do have to specify what sort of file handle we're going to read data from. But there's some standard file handles provided, like the standard in file handle, which will read from the keyboard. So yeah, that's why we're using fgets. That'll read in one line. And I guess the thing that I should do now is say line was, and print out that line. And I'm putting the string into square brackets here, just so that just so that we can see what the result was. Another thing that we can do is if we got back a null, if fgets returns null, that means we hit end of file. We're going to break out of this infinite loop and go ahead and just exit the program. Alright, makefile. Talked about makefiles a little bit earlier, but we're going to go ahead and write a slightly more complicated one here, because there are a bunch more source files. So I gave you one example of a makefile that's sort of reasonably straightforward. Now we're going to have an example of a makefile that is unnecessarily complicated. If you want to know how makefiles work in detail, go ahead and look at the manual for GNU Make. But here our sources are going to be what we get if we wildcard all the .c files in the current directory. The object files that we want to build are what we get if we take that sources list and replace every instance of a .c extension with a .o extension. Our headers are what we're going to get if we wildcard all of the .h files in the current directory. Now the executable that we want to build is called calc, and in order to build it we need those object files. and we're going to go ahead and compile in all our sources. That's not even right. We're going to go ahead and compile in all our objects. To build our objects, we need to have all our sources and all our headers. And these special variables do some magic of figuring out which object file goes with which source file. Right, then we need that .phony rule. So this may or may not work. I'm going to type make. So this compiles our program in 2 steps. First, it's going to compile each .c file into a corresponding .o file. When it's done compiling each C file into a .o file, it's going to link together all the .o files into our executable file. And this should keep working as we add more .c files, but we'll see if that doesn't happen. Now we have our calc thing, we run it, 3 plus 4, and the line that we get back is 3 plus 4 followed by a new line character, which we can see because we put the square brackets around. So that's fine. We have the line including the new line character. From there, our plan is we are going to tokenize, we are going to parse, and we are going to eval. Those are our steps. We're going to start off by tokenizing, and to do that, we're going to say we're going to have a list of our tokens is what we get when we tokenize our line. And we're going to have a file called tokens.h, which is going to define the list type and define the tokenize function. So we're going to open up tokens.h. Again, in a .h file, we want that include guard thing. And in here, what we're going to do is we're going to include our list.h file, and then say that we're going to have a function that returns a list called tokenize, which takes a string and returns a list, and this is a list of string, a linked list of string. Next thing that we're going to do is we have to implement linked lists. So now we're implementing linked lists. So a linked list is a string, which is the first item in the list, followed by a struct list, which is the rest of the list. So an empty list is a null pointer, and a list cell has an owned copy of the string it contains. So we're going to copy the string when we create a list cell. Now I think this list is actually the list that we had built previously. So let's actually go track that down in our previous code and save a little bit of time. So back here in our, we had a list of int before. So I guess we have to retype it. Before we had a list of int, now we have a list of string. I can type pretty quick. We want a print function for debugging and so that we can see whether this step of implementing tokenize actually works. We have a length function. We have a reverse function so that we can build lists that are forward. And we have a reverse end free function, which ends up being a useful utility function for what we're building. So next up, we're going to implement lists over in list.c. And we're going to take these functions and copy them over here. So we have cons, we have free list, we have print list, we have length, we have reverse, and we have reverse and free the old list. Cons. Okay. Other stuff we need in here. We need Studio for print list. We need standard lib for malloc. We need string.h for startup. We need list.h because that's what we're building, and that's where we have the definition of our list structure. So we're going to use malloc to create the new cell. We're going to create a copy of the string. And we're going to return y's. So the other thing that's going on here that we want to note is that consing a cell onto a list takes ownership of the tail of the list. To free a list, if it's not a null pointer, we free the tail, we free the head, and then we free the cell. To print a list, we're going to go ahead and iterate through the items in the list, and we're going to print out the strings. To get the length of a list, we're going to go ahead and iterate through the list and increment our return value every time we see a list cell. To reverse a list, we're going to start with an empty list. We're going to iterate through the input list. And we're going to cons each item on the input list x's onto y's, and that results in reversing the list. And then this rev_free function reverses x's, frees x's, and returns y's, which is useful for if we want to build a list that's forward, we can build it backwards and then return rev_free it. Alright, so there is our thing. Now we're over in tokens.h. We want to go over to tokens.c and actually implement our tokenize function. Right, tokenize is a function that takes one line of text and is going to return a linked list. And we're going to build up the linked list backwards and then reverse it as we return it. So the plan here for tokenizing is we're going to start by figuring out the length of the string. So we're going to need string.h up here. And then we're going to iterate through the string. So while our current position is less than the length of the string, the first question that we have is the character that we're looking at, the character II, a space? And to answer that, we're going to use this isSpace function. And we have this ctype.h header. And the ctype.h header defines a whole bunch of functions that, given a character C, we determine is the character part of this category. So we can ask, is it alphanumeric? Is it alphabetic? Is it a control character? Is it digit? Is it something that is a graphical character, so that it like prints? Control characters are not graphical characters. And one of the things in here is space. And this will determine if it is a space character, a tab character, a new line. And there's some other things that count as space characters that we don't need to worry about here, like vertical tab. But the one sort of funny thing here is that it takes an integer c. We're passing it a char, but a char is just a smaller integer than an integer, and this is from back in the day when people weren't going to a lot of effort to define functions to not take integers. It also returns an integer when it means Boolean. Again, that's a common practice in C programming. So this is a function of char to Boolean, but we have this this signature here. In any case, it works the way we want it to. So if we have a space, we're just going to skip that, and then we're going to use continue to continue to do the next iteration of the loop. Next question: if isDigit then we have a number. And we're going to call a helper function that's going to read a multi-character number into this string based on starting at the position II. We're going to cons that number onto our list. We're going to increase the II iterator, the position that we're looking at in the string, by the length of that number in characters. Num is a string, so we'll free it, and we'll continue. This does look like it's making an excess copy, but it makes things a little bit cleaner. Next up, if it isn't a space and it isn't a number, we know it's an operator. And further, we know that that operator is a single character, so we don't have to worry about having a read operator helper. So we're going to create a buffer on the stack, and this thing here is a 2 bytes. So the first byte is the character X, and the second one is the null byte. And that null byte is really what I want, because I'm going to replace this X with the operator, but we'll still have a null terminated string. So op sub 0 is text II. And then we'll continue on to look at the next character in the string. So now what we need is that helper function read number. Now we're going to figure out how long the number is. This isn't necessarily maximum efficiency because we're going to have to scan twice, but that's okay. So while we're looking at a digit, we're going to increase nn, which is our length of the thing. Then we're going to go ahead and allocate number of bytes on the heap equal to the calculated length of the number plus 1. That plus 1 is for the null terminator. And we're going to call memcopy into that buffer text plus IINN. So we're going to copy the number that we found here into the output buffer. We're going to null terminate it, and then we're going to return that number. So this now should work